I want to introduce Denis. He's a professor in our psychology program, and I'm very grateful to him for doing this session. We've been talking about it since June, and I'm really excited about it and appreciate that you all are interested in the topic as well. So thank you very much.
Thank you. Thank you, Amy, for organizing this talk, and thank you all for coming. This talk is not about statistics. It's about science, because we're all scientists here, yet we all use statistics. So what I've noticed in teaching stats to psychology students, communication majors, biology students, is that there's often a disconnect between statistics and science. Students are taught a whole bunch of statistical methods, but they're not quite sure how they relate to the scientific practice. So the purpose of today's talk is I want to run through about 10 things to look for in a research paper to see if there's anything there, or to see if it's maybe just a statistical smokescreen. So what I'm presenting today is not something that is extremely complicated, but it's something that you want to look for in a research paper to see if the goods are there. Okay. So what are the top 10 things? We won't get through all of them, and some of them we might discuss quite extensively, but what are they? Well, first of all, does the tested model make sense? Now, you might look at that and you may say, well, obviously that's one of them. Why are you bringing that up? And the reason I'm bringing it up is because often we look at research papers where the model just doesn't make sense. Parts of the model may make sense, but other parts should not even belong in the model. That's fine, you say. Just focus on the parts you like of the model and ignore the rest. Well, it doesn't work that way in modeling, because you could have a beautiful statistical model, and then we all know you throw in another predictor, and all of a sudden it's like being on the raft in the summertime when you're all seated on the raft in the water, and then somebody comes on, sits on the raft, and people bounce off. The whole statistical model can shift a little bit. It might not, but the potentiality is there. So we have to be aware of this when interpreting models. What we call that in the modeling business is what? Model specification. Is the model specified correctly? Because if it's specified wrongly, even a part of it, it can throw everything off. Let me just give you my take on how I perceive models and how I relate them to scientific practice. We can think of model fit as an overlap of data and theory. Students start out by learning t-tests. They go to ANOVA, they go to regression, and then they get into maybe multivariate methods, and then they end up in structural equation modeling, where structural equation modeling, finally it's revealed that we're looking for a fit between data and theory. Well, if we start out with that premise, data and theory, the goal of statistical modeling, pretty much any model, is to see how well the two fit. Now, I've got an overlap up there, but what works really well is if you just use your hands and you go, look, good fit. As George Box once said, what do we know about the fit of models? Well, they could fit beautifully, but all models are wrong, right? All models are wrong. That's the first thing I like to tell my stat students, to deflate them real good for the rest of the course, that whatever model you come up with, it's going to be wrong. Even if the model fits really, really well, it's still never going to be perfect. But nonetheless, we're looking for that fit. I love airplanes. So, of course, I look at the model airplane as the perfect model. We've got the model airplane. We're trying to approximate the population airplane that sits on the runway. Parameters of the particular population airplane that we want to estimate with the sample airplane. Well, maybe there's wing speed, lift, and a whole bunch of things that I know nothing about. But nonetheless, we have our sample model. We have statistics on that sample model, and we use those statistics as estimators to estimate what's really going on in the population. There's two things to modeling, really. There's estimation, and then there's the structural model. Well, if I look at the structural model, I can look at it and ask myself, how well is this representing what I wish to study in the population? And that we can loosely look at as the specification of the model. But then there's the estimation of components of the model. So when I compute a statistic on the model, I'm using that statistic usually as an estimator of the population value. We do not care about statistics. That's another thing I like to tell my stat students is the book shouldn't be called statistics. It should be called parameters. Okay? We care about parameters. Why don't we study parameters? Too expensive. Populations are too big, so we settle for studying statistics. Use them as estimators of the parameters. But realize that whenever you look at a statistic, whether it's the sample mean, whether it's the sample variance, or a whole bunch of other things, we're really not interested in those things. What we really want to know are the parameters. It's a good thing to keep in mind. Understanding ANOVA and regression is the gateway to understanding many advanced statistical models. So ANOVA and regression pretty much do the same thing, but go about things a bit differently. Nonetheless, a good grounding in those two approaches makes other things seem much easier and kind of demystifies them. I like demystifying things. When I look at a multi-level model, for instance, random coefficient model, mixed modeling, at first they can seem very, very sophisticated until you look at them a little bit deeper and you just realize that, oh, it's just really an extension of the basic grounding in ANOVA and regression theory. All statistical models that predict a response have a random component associated with them, E, which is theoretically made up of an infinite number of things, one of which might be called chance, if you're so inclined to believe. If you're that religious that you believe in chance, go ahead. Some people might think that chance doesn't exist, so what is the error term made up of? Well, we can say that the error term is made up of all those things that are not included in the model, that have an effect, put effect in quotes because that's really important, have some kind of effect on that response variable. So if we look at the ideal scientific model, it would be nice if we can say y equals x, or x plus 3, or x plus other functions as well. That's OK. But the realistic statistical model is that it's y equals x plus e. And this is the joke that everybody likes to say. E is one researcher's error term, another's career. There's actually more to that joke than it seems, because I actually sometimes ask my students that by the end of the course. I tell them that joke, and the ones who laugh, I know get it. They got the course. The ones who don't figure, okay, you need a little more studying to understand what this means. Okay? So a whole bunch of people out there trying to break up that error term. Somebody comes up with a randomized block design. Try to get at the error term, try to piece it apart. Somebody in a regression approach tries to put in another predictor, partial out that predictor, or heaven forbid, control for the predictor. Control is something we're going to talk about as well. Well, there's the analysis of variance model. There's the ideal situation. I always like to start off with the ideal and then see how much I fall from the ideal. So that would be a nice idea if we had 4 different teachers. We were measuring, say, achievement data on them. And if the data came out like that, we would have trouble constructing our F-tests, but that's a nice setup. No within variation, between group variation. We can see that there's an effect. We don't need statistics to address this. We can see there's something going on. If I look at the less ideal situation, well, there I have a bit of a mess, and I have that within group variation, and I still have the between group variation. So what does analysis of variance actually do? Well, analysis of variance asks the question, fundamentally, why are scores the way they are? And I think that's a good starting point to understanding modeling. So if I look at this, I literally want to know, why is 70 the way 70 is? Why is 67 the way 67? Why isn't it something else? So what do? Well, we try to theorize as to why the scores are the way they are. And this is the start of building the model. So I look at 70 and I say, well, 70, what could it be a function of? Well, they all receive the same teacher. Let me put that slide back up. They all receive the same teacher, so it can't be because they had different teachers as to why this person got 70. But this one's 70, this one's 67, this one's 65, so there's some unexplainable variability going on within the group. And I know most of you already know that. I'm just reviewing this to get the feel for, get us into talking about models and things. But there's that within group variability that's unaccounted for. When we bring in other predictors, other factors into the model, it's essentially to get at that within group chance variability so as to get a better prediction on y. So we can use, in ANOVA theory, we can use identities such as this one, which is the breakup of the sums of squares. So I have y sub ij, individual I in group j, minus the grand mean, is equal to the within plus the between deviations. We know that if I sum those up, I'm not going to get a very nice number. I'm going to get 0, so we're going to square the deviations, which leads to the partition of the sums of squares. SS total is equal to SS between plus SS within. There's the arithmetic of ANOVA, and our theory is that a given observation in a given group is equal to the grand mean, so the overall mean, plus the effect, there's my treatment effect of being in a particular group versus another group, plus the error component. Okay? So there's our ANOVA model, and there's the summary table for ANOVA. A couple comments on the summary table for ANOVA. Again, this is all falling under the umbrella of is the model specified correctly. So we're just reviewing a few modeling principles. So when you look at the research paper, you can say, well, do I trust the model? Is it reasonable? Here's our sums of squares between, within, total. We have our degrees of freedom. Now, one thing, you can get a lot of information from this table. One thing to realize is you can think of this as the descriptive part of the ANOVA table. And then once we go over the bridge of the degrees of freedom, I like to call it, once we go over the degrees of freedom, we get the mean squares, and that's where we get into inference. So there's a reason why when we talk about eta squared in ANOVA, we are not taking MS between over MS total. We are taking SS between over SS total to give us our measure of effect size. And that's another thing I want to talk about is the difference between effect size and the p-value, because that is extremely, extremely important. We get our F ratio, and what's the question we ask on F? What's the probability of U? What's the probability of getting an F like this? Again, I'm not talking too formally, but it's just to get the sense across. What's the probability of getting an F like that? If it was born out of a distribution on j minus 1 and n minus j degrees of freedom. Why do we want it to be less than 0.05? Well, 0.05 is completely arbitrary, but why do we want the probability to be low? Because if we get an F that falls off into the tail of the distribution, that means Fs like that don't happen very often under the null hypothesis of equal means, equal population means. So there's the classic ANOVA table, which we can adjust for regression problems as well. One thing to keep in mind when you are looking at the research report, you want to know if the factors are specified as fixed or random. What's a fixed effect? What's a fixed factor? Well, if I look at my table again, and I'm only interested in comparing the means of teacher 1 versus 2 versus 3 versus 4. Those are the only 4 teachers I like to study, and I want to make conclusions about, then teacher is a fixed effect. So I'm only allowed to make mean comparisons. Now, would this be a fixed effect, or would it most likely be a random effect? Well, if I'm interested in the achievement scores for different students across different teachers, I'm probably not interested in just those 4 teachers. More likely, I'm probably interested in a population of teachers. So where teacher becomes a random effect is if I actually randomly sample teachers for the study. So theoretically, if I go into a bin of teachers and I pull out 4 out of a population, that becomes random. What's the advantage of treating it as a random effect? Well, the advantage is that if I find differences, variance explained between teachers, I can say that that's true about my sample data and teachers in the population as well. Okay. So you want to look for in the research paper whether the effect is fixed or random, because that's going to have huge implications. It's going to have implications for how the F ratios are constructed, but most importantly, it's going to have implications for what the conclusions are in the discussion section. More times than not, what we see in result sections and discussion sections is people start off with the fixed effects model, so they only say they're going to talk about these 4 teachers, and then what's in the discussion? They say, therefore, there's different amounts of achievement for different teachers. Well, that's not true. There's different amounts of achievement for these particular teachers if it was specified as a fixed effect. So that's important to see if it's fixed or random. Models are context dependent. Okay, and I talked about this just a little bit a while ago. It's saying that, what do I mean by context? I mean that if you have the model, it matters what predictors are in the vicinity of the model. So model 1, A predicts B. Okay, so we find a statistically significant regression effect, et cetera. Model 2, A does not predict B, given the context of C. So what happened? Well, first I had a prediction, and then I put in C. Oh, prediction's gone. So what's going on? Well, what's going on is just the partition of variability. But this becomes really hard to understand and really hard to explain to a biologist that, you know, something had an effect, but if you put in another variable into the statistical model, all of a sudden the effect disappears, and we know that psychologists love that, because what's the second model? Mediation. Right? If you put in that other variable, well, the prediction disappears, then we can say mediation. Well, maybe we can say statistical mediation, but a little bit harder to talk about substantive mediation unless you have an argument outside of the statistical model. So that becomes a little bit tricky, and I'll talk about this more. You can't just look at a statistical model and say, hey, I got statistical mediation, therefore, hey, I've got a physical process going on there. X is pushing Y around, and Z is interfering like a mediator and going, you go there, you go there. You have to have the physical base for doing that. You can't just rely on the statistical model. What's the ideal model? Well, A predicts B given the context of the universe. I guess that's the best model. So does that mean controlling for the universe? Or does that mean ignoring the universe? I don't know. I don't know. That's kind of beyond my ability to know. But if you have all the variables in the universe and you're looking at the regression in question, that's the ideal model, because then you know that you've accounted for everything else that could be acting on that relationship. I often like to ask students, if you correlate height and weight, is that the true correlation between height and weight? So if I bring it to the media, I say if Anderson Cooper on CNN asked you, is X correlated with Y? What would you say? You'd say yes. But then if you put in other variables, you see the change in correlation, so what's the right answer for Anderson Cooper? Do you tell them it's correlated, or do you tell them it's not? Well, you're going to have to go to saying, well, there's a zero-order correlation, but partial correlation is going to change, and you have to bring in all these things. What I'm getting at is the truth of what we're talking about is actually pretty hard to get at when you take it outside the statistical realm and think about what it actually means scientifically. What does it mean scientifically? And that's the harder part. When you change the model, you change parameter estimates, you change statistical effects, you may not be changing real effects. If I take a balm and I put it on the wound and I watch the wound heal, I don't care too much about what the statistical model is going to tell me because I know the wound is healing. So if somebody shows me a statistical model and says, you know, if I put in another predictor, all of a sudden I'm not seeing that effect. I'm seeing some kind of mediational effect. Well, I still know that the balm is curing the wound. So I can interpret the statistical model, and I also have the reality-based phenomenon going on, and I could see how well they agree with one another. What's the problem with a lot of social research? A lot of social research isn't as clear as having a wound. You can't see the wound. You have to rely on constructs. So what I like to say is sometimes a lot of modeling in a lot of the social sciences is model dependent. Does self-esteem predict future success? Yes. Let's say, I don't know. And then you put in another variable, oh, there's a mediator. Well, how do you find that in reality? It's not like looking at the wound and saying, I can match it up with the wound. So what I'm saying is that if all statistical theory went out the window and we kind of gave up on it, we said, my God, what we've been talking about is complete BS, we still have recourse to the physical model in situations. In other situations, we're dependent on the statistical model, and we should be aware of that. So when we're looking at the research paper, ask yourself, are the effects statistical, and do they match something in reality? Statistical models, even if specified reasonably well, may not correspond to processes in reality. You are never, ever testing individual effects in the model, no matter how simple the model may be. T-tests are context-dependent, as are SEM models, as are simple correlations. So again, to reiterate, if I do a correlation between X and Y, your argument may be that the model is incorrectly specified. Why? Because I did not include another variable that would have an effect on that correlation. So it's fair to say that even the simplest models may not be correctly specified. You're always testing the model, and hence the interpretation of parameter estimates must be within the context of the model. My favorite thing, my students can attest to this, that I love to grade them bad on their tests is that if I give them a multiple regression model with x and z predicting y, and I ask them what the effect is of x predicting y, if they don't say given the presence of z, then they don't get the point. Because what are they doing if they just say x predicts y? They're interpreting the bivariate effect in a more multivariable setting, which we know from mediation, moderation, and all that, may not hold. So we have to know the context of the model. Watch out for research papers that make those conclusions. X predicts y, period. X does not predict y, period. X predicts y given the model that is being tested. Really, really important, no matter how simple the model may be. Polynomial possibilities. Again, we're still under number 1 of the heading of what to look for in a model, see if it's specified correctly, does the model make sense? And whether it makes sense fundamentally comes from your substantive expertise. So you're looking at it carefully, you're inspecting it first, because if it doesn't make sense, forget about all the jargon, the statistical jargon, because you can just kind of throw the paper aside. Polynomial possibilities, most models assume linear relationships. I think it's very reasonable that a lot of models assume linear relationships, because I think it's really hard to get nonlinear relationships in a lot of fields. And if we can at least approximate something by a line, we're doing pretty good. But it's still worth investigating a little bit, looking at it a bit, saying, why are they assuming linear? Now, the classic example of nonlinear relationships where things really are linear is when you just have a certain selection of data points that happen to be a different curve. And then all of a sudden you press trend analysis in SPSS and you go, oh look, it's doing this. Well, that could just be sample fluctuation. I doubt you have a cubic relationship there. You're probably better off with just saying it's linear. That gets to the idea too that we can fit data points, we can fit lines and curves to data points beautifully and have all kinds of complex curves, but the goal of science is to summarize the data knowing what we know about the background area of the research. So be aware of too complex of curves fit to data and ask yourself, does this really apply? Is this really a sign relationship we're seeing here, or is it really some kind of linear relationship and they're capitalizing on chance? There's the Challenger data as an example of a nonlinear relationship. There's temperature of the O-rings. When the O-rings failed on the Space Shuttle Challenger, they found out that with the number of incidents that happened with the O-rings expanding, well, it's a function of temperature. So that if you have high temperatures, you might have more incidents. If you have low temperatures, you might have more incidents. Not a lot of data, but you can see why the Challenger exploded at low temperatures, launched at, I think it was 51 or 53 degrees, where there's a lot of failure. Chance of failure was relatively high. Pearson R, another thing you're looking at in the research report in terms of under the model, the general model. If you come across Pearson correlation coefficients, remember they capture linear relationships, so you're always looking for a plot. Okay? Always look for a plot. If I give you an R coefficient and I just say R is equal to 0.60, well, what do you know? You don't know much until you look at the plot. Okay? Likewise, if I give you a correlation coefficient, say a small one, you say, this does not mean there's no relationship. It means it doesn't look like there's any linear relationship. There may be something really, really wicked going on in your data that this isn't going to capture, because if your data look like this, R, by the way it's defined, is going to try to do something like that, and it's going to give you a low number. So never accept the statement in a research report that there is no relationship simply because there is a low Pearson correlation coefficient, and always look for a plot. There's our Pearson R there. Okay, still under the topic of models. We will get to number 2, I promise. Multivariate models. Okay? So you're looking at the research report, and you're seeing that they tested a multivariate model. Well, is that good or bad? Are multivariate models worth it? Well, the first thing is that they only make sense if they make good scientific sense. This is something I like to stress a lot, because I often see this, it's not a competition, but the more sophisticated the discipline of statistics gets, the more the scientist feels as though they should be using these methods, and they really look good at job talks because they're doing latent variable modeling rather than ANOVA. But I think we need to ask ourselves, does the multivariate model make sense? If it doesn't make sense to use for the scientific problem, I don't think we should be using it. So I think we should beware of misleading rules of thumb. The classic one is MANOVA. Here's a rule of thumb for MANOVA that sometimes people like to give. Use MANOVA when you have more than a single response variable. That's absolutely false. Statistically, it's absolutely nice. And if you have correlation among the response variables, sure, go ahead. MANOVA will control your type 1 error rate and all these things. But as a scientist, what is that statement telling me? Use it when I have more than a single response variable. Even if they're continuous variables, does it make sense? So if I draw a function statement up here where I have my y variables here and my x variables here, if I put y1 and y2 in a model, I'm looking at a MANOVA model there. If I have a categorical predictor, so there's my x with, say, 3 levels, what's the justification for doing MANOVA? It's not that I have 2 variables. It's that these 2 variables, theoretically, according to my theory, generate a meaningful linear combination. And if they don't generate a meaningful linear combination, I shouldn't be doing multivariate analysis of variance. I'm probably better off with doing univariate analyses on each y. So if y1 plus y2 doesn't make sense theoretically, like if I'm studying self-esteem and how many times my dog barks, well, that's not going to make a lot of sense. So you want to make sure that they go together. So I think when we're looking at the research report, we want to see, okay, they did MANOVA. What's the variate? What's the dependent variate? What's the linear combination they're talking about? And if they're talking about a linear combination, a variate that you don't agree with, or you know the research area and you say, that doesn't make sense, that's a foolish linear combination, then MANOVA is the wrong strategy. Of course, if you are doing MANOVA, it has many statistical benefits. And one of the statistical benefits is it does capitalize on the correlation among variables. It could afford more power in some situations. And it'll help control your type 1 error rate. So instead of doing 2 univariate analyses, you just do this one, and you set your type 1 error rate at, say, 0.05, and you have control over it. But again, the statistical benefit should only come into play after the scientific benefit is accepted and realized. It doesn't make sense the other way. That's why I don't think it's right to say we do MANOVA because we have more than a single response and we want to control type 1 error. No, you do MANOVA because it makes sense. Oh, and here are the statistical benefits to doing it. I think that's important. We can say that when you perform a MANOVA, you're testing a different null hypothesis than when you perform separate univariate ANOVAs. And that just should not assume that the rejection of one hypothesis, the multivariate hypothesis, automatically informs you of the status of other hypotheses, univariate hypotheses. Likewise, you should not assume that individual univariate findings on separate response variables will necessarily generate a multivariate effect if combined. There's something known as Rayo's paradox in there, saying that you can reject multivariately but fail to reject univariately, and vice versa can work as well. So we have to get out of this thinking of talking about the multivariate effect as decomposable into univariate effects. And again, how can we think about that? We think about if this is the correct model to test, then test it. If you follow up the model with univariate effects, those univariate effects should make sense from a theoretical point of view. You're not really chopping up the effect. One more note on multivariate models. Sometimes students look at multivariate stats and they go, oh my God, that's like a whole different thing. I don't want to take the course and I don't want to do multivariate methods. But really, there's a simple extension of the univariate models. So if we look at a t-test, and here's a t-test, independent samples group t-test, where we're subtracting constant of 0. So we're looking at a mean difference between 2 groups. Those are population means, but I'm taking the expected values, so they're really samples. There's my pooled variance down there, and I'm going to do my t-test. So we're all familiar with the t-test. Once I get into the multivariate domain, Well, then I'm looking at the covariance among response variables. So there's my multivariate domain up here again, where as soon as I add another dependent variable, I'm looking at covariance between these. So if I take away this and I have two groups on this vector now, this is the vector. If I have two groups, well, then I'm into Hotelling's T. But look, Hotelling's T is actually very similar to univariate T. Here are my vector differences right here. That's the transpose. So I'm squaring it. That's all that is with this. And there's S to the -1, which is the inverse of the variance-covariance matrix. What that really is just take these vectors and put this on the bottom in the denominator. And that's going to be an expression of variability and covariability, very much like this denominator is an expression of variance. So really, we're doing something a little bit different because we're getting the covariance between response variables, but really it's not that different than the univariate T. So when you're looking at the multivariate methods, always ground yourself in the univariate ones and just see them as extensions to it, extensions of the fundamentals. There's number one. So number one, does the model make sense? If it doesn't make sense, then the rest of the paper could be suspect. Number two, again, second thing you want to look for in a research report, is the design an experimental one or is it non-experimental? I tend to favor experimental designs. I know in a lot of survey research, I mean, there's no way of having the experimental design really. You need to gather data, correlate data. But I think that's one of the central things to look at. Is it experimental? Is it not? What are the consequences of it being one or the other? Statistical analyses can be used to analyze experimental or non-experimental data. Example, ANOVA is not experimental and regression is not correlational. Sometimes investigators think that if you're doing an experiment, well, then you should be doing ANOVA as the analytic process on there. But really, you can do regression just as well. Okay? The actual reason why ANOVA exists as a statistical methodology is largely for convenience. Regression came about in the 1890s or so, multiple regression. And had we had computers back then, this would have probably not arose. So it's computationally efficient. It was easy to partition. But had we computers in the 1890s, it wouldn't have had the same onset as it did in the 1920s. ANOVA was really big in the 1920s with R.A. Fisher. So the thing is when you're looking at it, at the research paper, if you see ANOVA, if you see regression, do not assume that one is experimental and one is correlational. You need to know the design, not just the statistical procedure. Second thing here is, does the word cause appear anywhere in the research? Does the word cause appear anywhere in the research? For me, at least, being a bit of a methodologist, when I see the word cause, I'm like, all right, I can't wait to read the rest of this to see what causes what. And I'm not even that philosophical. I hate to go to the philosopher and say, hey, I got a paper here that says that X causes Y. Care to analyze it? And I can just imagine what they're going to do with it. You're going to tear it up and go, where's the causation? First of all, what does the author mean by causation? Because we know that philosophers of science study causation repeatedly, and they still have trouble with understanding what is causation? How do you specify causation? So causation is really, really difficult. And I can't even explain it because I don't know what it is. So if somebody writes that in a research paper, I'm curious to see what their justification for it is. Does the word cause appear anywhere in the research? And if so, is it justified? That's the point I was just making. Now, one thing that we see in research papers is this idea of causal modeling. Well, what's causal modeling? I come down hard on this. I've looked at some of the history behind this, so I know a little bit of where this traces from. And when I see the word causal modeling, I just think of it kind of as a myth. It's kind of like the Sasquatch. It's like, that's not real. That's not real. It can't be causal modeling. Where does this come from? Well, if we look at the history, we see that the words causal modeling originated more or less in regression history, but more so in the history of path analysis. Wright was a geneticist who studied, among other things, guinea pigs, and he developed the procedure of path analysis, and he called the coefficients in the path analysis causal coefficients. They were path coefficients, and he called them causal. Well, that ignited a whole debate. And people were saying, well, you can't prove causation just because you choose to call the coefficient causal. Well, then Sewall Wright said, well, look, I'm working with guinea pigs. Okay? These are the guinea pigs. And he was interested in problems of heredity. Color of the guinea pig. If you mate the mama and the papa, what color does the little baby guinea pig come out to be? So in that sense, it wasn't a sin, methodologically speaking, to call those coefficients maybe causal coefficients. I mean, if you take the mommy and the papi guinea pig and they mate, the baby guinea pig is going to be of a certain color. And I think it's reasonable to say that there's some kind of a causal effect that's producing the color in the baby guinea pig. So putting coefficients on these arrows towards the babies here could make some sense if you call them causal coefficients. But what happened after that? What happened after that is people started using this method of path coefficients and path analysis, and they brought it into their area of research. One of the first studies to use path analysis was one by Birks in 1928, and this one looked at parental intelligence and environment causing children's IQ. Well, there again, it was reasonable to put coefficients here and to maybe refer to them as causal coefficients and to call the whole thing a causal model. Why might it be reasonable? Well, maybe because that's the theory at the time, probably still is today pretty much. There we say parental intelligence, you have environment, nature-nurture debate. It made sense. But what happened after that was the economists, social scientists came around and they took this causal modeling methodology, and what happened with it was that all of a sudden you could have X, you could have Y, and you can say they're causing Z. But why doesn't that make sense? Well, you can put a beta coefficient here, you can put a beta coefficient here, but this is only going to make sense if what? It's only going to make sense if this makes sense, if it's a causal model. So you cannot take non-causal variables, throw them into a causal model, and then claim that X causes Z. Just doesn't make sense. So what can we say about this? We can say that before you use path analysis or causal modeling, which is overachieving offspring is structural equation modeling, that you have a causal context to the design before you start calling it a causal model. Otherwise, what is it? It's a regression model. It's prediction. So I think we should look for in research to see if they overstate the conclusions on the coefficients that they make. So I'd like to say that statistical model plus causal context equals causal modeling. Statistical model plus non-causal context equals non-causal modeling. Okay. Related to that, we'd like to look for, are there any directional or action statements used? And do authors justify why they're making such claims? Mediation or moderation hypotheses usually not confirmed by statistical tests. Moderation's a little bit more on solid ground because it's interactions. But mediation, there's lots of room for philosophical debate there. And we need to really be aware of this. I talked about it a bit earlier, that if I have my IV predicting the DV, or if the researcher might even say cause, again, look for the justification as to why they're saying cause. You can't say cause just because they're using a mediational model. When I throw in my mediator and this drops down, ideally to 0, well, what does that mean substantively? We can call it statistical mediation all we like, but substantively, what does it mean? And that's the harder part. So we need to be aware of that, I think. Was factor analysis, cluster analysis, or principal components used? I'm not going to talk very much about that, but were claims regarding their capabilities overstated? None of these procedures discover substantive factors or groupings. Oftentimes we think of factor analysis as uncovering. Think of like uncovering something in the dirt and then going, the factor right there. But really they don't uncover, they don't discover, they correlate. They correlate. So take a bunch of variables, correlate, reduce it down into components for principal components or factors in factor analysis, but there isn't any discovery, ontological discovery of any substance, just correlations put in a different way. Is the research statistically loaded but scientifically slim? Is the research merely a work of statistical art? Example, numerous specification searches and lots of statistical jargon to make up for a weak scientific effect. What I think about that is sometimes researchers will test, it usually happens in structural equation modeling, where they'll test a model and then they run these specification searches on the model. They change parameter estimates. They fix, they free, they fix, they free, until the model produces a nice fit. And then, of course, that's when we say, hey, this thing's ready for publication. Get it in the paper, right? So is there a lot of that going on? Has the author been honest about how many times they ran their model? If they ran their model 1,000,000 times and are presenting the model that works, well, I think we need to be suspect about it. How theory-driven was the construction of their model, and how theory-driven was the estimation of the parameters that they chose to estimate? Number 3. Number 3 is a really, really big one. I don't know how much people know about this issue, but I really want to stress this. If you take away one thing about this talk today, I think this should be it, because it's really important. Are p-values and p-values alone used to justify a finding of sorts? Do researchers mistakenly equate p-values with effect size? The first thing is they're not the same. R.A. Fisher came up with the analysis of variance procedure in about 1925. A fellow by the name of Berkson, 1937, said, you know, the observant statistician actually realizes that they can get statistical significance if they just increase what? Sample size. If you just increase sample size, you can make p as small as you want, so long as there's some effect. If there's no effect, forget about it. It's not going to happen. But if there's some effect, just boosting your sample size will get you p is less than 0.05 or whatever number you want. Must be a problem with the significance test. No, the significance test is working just fine. It's doing its inferential job. In the math stats building, there's no problems with the significance test. In the science building, there is a problem, because when we look at the significance test and we try to conclude something about our research, that's where the bridge isn't that smooth. And methodologists have known this for years, and there's a whole litany of research on the p-value, problems with interpreting p-values, how to interpret them, problems of inferring things from p-values. Yet it still goes on where we see results in journals and things where we see p is less than 0.05, and that's somehow evidence for an effect. The medication is effective, p is less than 0.05. Well, scientifically, perhaps not that meaningful. Statistically, very interesting. Statistical significance is statistically interesting, but scientifically boring. It's just boring. So I don't mean to bring us down. But when we see this, the first question you should ask is, well, first observation you should make is, so what? If they're not giving you sample size coupled with this, you have no idea what's going on. What does this literally say? It means there's some difference in your sample means, to take the example of a t-test. There's something going on in your sample. Now, if I give you a sample size of, say, n equals 50, if I couple those two things together, then what do you start to think? Start to think, oh, maybe there is something going on, because probably the p-value isn't being deflated by simply the sample size. But of course, we can look at effect size. We can look at statistical significance in conjunction with one another. So we don't have to just arbitrarily guess at it. P is less than 0.05 is way overrated. P is less than 0.05 tells us the probability of some data given a hypothesis we already know is false before we were born. Do you get the point? I try to make the points I believe in very, very clear and kind of overstated. Everyone clear on why it's false? It's false because if I have two parameters, look, think of what the null hypothesis test. HO mu1 is equal to mu2. What a stupid hypothesis to test. We know it's false to begin with. You really think in the population, for whatever you're measuring, that the two population means are going to be equal? Not a chance. They're going to be unequal, and if they aren't unequal, carry a few decimal points, and I guarantee you they'll be unequal. So already, we know that when we look at this hypothesis, we know that it's going to be false. So problems abound with null hypothesis significance testing. The example of the medication is effective is a somewhat empty scientific statement if not coupled with other information. And you can see too where if you're not aware of the influence of the p-value in the construction of it, it can be easy to get results by someone if they tend to believe that this by itself is valuable. Because you can just say, well, let's change the policy decision because I found an effect if p is less than 0.05. Well, if the receiver of that information has been taught that p is less than 0.05 equals good, well then they're not going to know. Recipe for getting p is less than 0.05, adjust according to taste. This is just a few examples put up here. Well, there's a z-test for means. So we got our sample mean up here.